Hello students, welcome you all to the next session regarding discussion of the analysis of turbo machines continued part. In the last session, we have discussed some of the problems with respect to the axial flow turbines. In today's case, we'll be discussing some of the problems with respect to the radial flow machines. So what will be the conditions for the radial flow machines at the inner velocity triangles as well as at the outer velocity triangles? And with respect to the conditions, how the shape of the velocity triangles they get changed at the inlet as well as at the outlet as per the conditions given in the problem. So right now on the screen you can see my email IDs which you have. If you have any queries, you can send me an email to this email IDs. Also, you can send me a WhatsApp message to this WhatsApp number also, students. Okay. So now let us begin the session. So the question given to you is, here it says there is an inward flow turbine which is having an inlet angle of 20 degrees. The water leaves radially. Then the speed of the wheel is 350 RPM and the velocity of flow is 4 meters per second. Inner and outer diameter of a turbine are 30 centimeter and 60 centimeter respectively. Width of the wheel at the inlet is 12 centimeter. Find the blade angle and power developed. Also, what will be the value of R, which is given right now here. So as I told, whenever you are solving the problems of turbo machines, every word has to be analyzed carefully because maximum number of conditions are given in the statement itself. So initially it says there is an inward flow turbine, which means the flow is towards the shaft, that is the inlet directions. And it says an inlet angle of 20 degrees. So inlet angle of 20 degrees in the sense alpha 1 is equal to 20 degrees. Then he says the water leaves radially. So the water leaves radially in the sense this radial is there for the entire system, that is the inlet velocity triangle as well as the outlet velocity triangle. Water leaves radially. Just I will write here this condition such that when I draw the velocity triangle, I will tell you how the water is leaving radially at the inlet as well as at the outlet. Water leaves radially, which means it is the components they are overlapping on the axial velocity components, flow components. Then it says speed of the wheel is 350 RPM, that is the value of n, which is given here, 350 RPM. Then he says velocity of flow is 4 meters per second. So already he has given the word that is radial in the problem, which means the velocity of the flow at the inlet and outlet is constant according to this question. So Vf1 is equal to Vf2, which is equal to 4 meters per second. Then he says inner and outer diameter. Please remember, students, many times in the examination, what you do is inner means the suffix you are writing it as 1, outer means the suffix you are writing as 2. But whenever he gives the problem of an inward flow turbines, please see that you draw the rough sketch such that you can understand the particular problem. So suppose students, this is my inner diameter. I will name it as diameter. D is equal to, it's around how much inner diameter values? 30 centimeter as per the given statement in this question. Then outer diameter. This is my outer diameter. Its diameter is how much? 60 centimeter. Please observe here this statement carefully, students. Then he has said that the width of the wheel, we are writing it in the form of symbol as B. It is around 12 centimeter. He has asked us to find out the blade angles. Blade angles in the sense we should find out here a beta 1 as well as beta 2, the blade angles. Then power developed, we need to find out P, and the value of R, it has to be estimated. Whenever the case of a problem is given the diameters, please observe or draw a rough sketch at the side of your sheet such that you can understand which is the outer diameter, which is the inner diameter. Now, my question to you, students, he has said that it is a case of an inward turbine. So for inward turbine, we have this already said that the flow is towards the center. Do you agree? The flow, it is towards the center. It is in this direction now. So now this is my center axis. This is my center axis, and the flow which is there, it is the flow, the water which is entering, it is entering where? First, where it enters? It enters at the outer diameter, students. Then it passes through the turbine blades. It passes through the turbine blades, and after passing through turbine blades, it is coming out through which diameter? The inner diameter. Yes. So now, if you observe here carefully, at this particular point, which I am highlighting here, that is the pink color structure which I am highlighting here, this particular point, the water is entering here, which means now this becomes your D1, even though it is outer diameter. At this point, the water is entering in the turbine now. That is the reason that it becomes D1. Similarly, it passes the turbine blades and through the inner diameter, it is coming outside. That is at this particular diameter, it is coming outside now. So this becomes your D2. This is very, very important. Many times what you do by default inner, he has said you write it as a D1. D1 is equal to 30 centimeter, D2 is equal to 60 centimeter. If you write this one, you lose the entire marks. That is the reason that I have written this statement and I have drawn this sketch here. So now according to this particular sketch, the value of D2, it is 30 centimeters. Similarly, the value of D1 is 60 centimeters. Okay. Now, once these things are clear, we can draw the velocity triangles. But before I draw the velocity triangles, one thing I would like to show you is regarding this statement, that is how the water leaves radially for the inlet and outer velocity triangle. So just I will draw the inlet velocity triangle. Please observe here. This is the generalized structure which we are preferring from the inlet velocity triangle. Okay. This is V1, alpha 1. Here we have VR1. This is beta 1. Then this I have VF1. Then from here to here, we have U1. As both the diameters are different, so automatically even in this problem, the tangential speeds always will be different. VU1. Okay. Now, when the water is leaving, the inlet velocity triangle, he says radially. So if you observe the question carefully, already one hint is given in the question that water is entering the velocity triangle with an angle of 20 degrees, which you can see here, which means alpha 1 is 20 degrees. Then the water, when it is discharging out, that is this particular value, beta 1, it is radial, which means this particular term VR1, it overlaps on VF1. So when this overlaps on VF1, the new velocity triangle, it is in this fashion now. Please observe here. This is my new velocity triangle. This is the value of V1. Then here VR1 is overlapping on VF1, which means VR1 is equal to VF1. And now this is alpha 1, 20 degrees. And when the water is leaving a radially from the inlet velocity triangle, the value of beta 1, what happens now? It is a right angle that is equal to 90 degrees. And therefore, here what you can say, U1 is equal to VU1 in this case. U1 is equal to VU1. This is the condition for inlet velocity triangle, students. This is the condition for inlet velocity triangles, which I have shown here. Similarly, even for the outer velocity triangle, I will show you here now. Let us see here. This is my outer velocity triangle. This is VR2, angle beta 2. Then I have V2, angle alpha 2. Then I have VF2, From V2 to VR2, I have the tangential speed U2. Then V2 to VF2, I have tangential component of the absolute velocity, that is VU2. Here also we are saying that from the outer velocity triangle, the water is also leaving radially itself. So here in the outer velocity triangle, when the water is leaving radially, this particular velocity factor, that is V2, it is overlapping on which one? VF2. So when this is overlapping on this particular velocity triangle, the new triangle which is forming after the conditions is, it is in this fashion, that is VR2 remains here itself with an angle of beta 2. By the overlapping of V2 and VF2, we get it as V2 is equal to VF2. This is the water, the fluid leaving radially, that is alpha 2. And now here in this case, this is U2. As VF2 is overlapping on V2, so therefore VU2 is equal to 0 with alpha 2 equal to 90 degrees. So please remember, students, when the water leaves radially from both the inlet and the outer velocity triangles, in the inlet velocity triangle, beta 2 is equal to 90 degrees, whereas in the outer velocity triangles, alpha 2 is equal to 90 degrees. The condition is the water should leave radially from both the entire systems, that is inlet velocity triangle as well as the outer velocity triangle. So once we are familiar with this one, let us begin the solution of this particular problem now. Yes, I said alpha 1 is equal to 20 degrees, water leaves radially, that is alpha 2 is equal to 90 degrees, n is equal to 50 rpm. Then this water leaves radially, I have said it leaves radially throughout the system. So we can write directly for outer velocity triangle, but once we alter the changes for the velocity triangle, we can take their beta 2 is equal to 90 degree also. Velocity of flow is constant, Vf1 is equal to Vf2 is equal to V2. Then I said with respect to the diameters, please be very careful. That is the reason that I had drawn the sketch of the diameters. And the inlet velocity triangles, if you observe, it is in this fashion. Similarly, the outer velocity triangle. So in the inlet velocity triangle, you can see U1 and VU1 both are the same, whereas in the outer velocity triangle, VU2 equal to 0. Now, another important point here, students, we have said that Vf1 is equal to Vf2 is equal to V2. So Vf1 is equal to V2 is equal to Vf2. But according to sketch of the inlet velocity triangle, even Vf1 is equal to what? It is also equal to VR1. Is also equal to VR1. Please remember this statement. Now, the solution part, yes, you can see here, we are having the tangential speeds for both the velocity triangles, that is the diameters are different. So we find out the value of U1 is equal to pi d1 n by 60. We get the value of U1 as 10.997 meters per second. Similarly, we find using the trigonometric functions, we find the sine alpha 1 for the inlet velocity triangle, that is this particular velocity triangle. Sine alpha 1 is equal to Vf1 is equal to Vr1 by U1 or Vf1 V1. We get the values V1, we get the values as V1 is equal to 11.6952 meters per second. So if you prefer this inlet velocity triangle with the sine alpha 1 is equal to, this is the opposite side, Vr1 or Vf1 you can write divided by V1. So on substituting the values and on simplification, I get the answer as V1 is equal to 11.6952 meters per second. Similarly, I go for outlet velocity triangle. For the outlet velocity triangle, you can take the hint of Vr1 is equal to Vf1 is equal to V2 is equal to Vf2, which is value is available. You can calculate the tangential speed U2 is equal to pi d2 n by 60. Once you have both these values, you can go for finding the value of Vr2 also. So tangential speed I have found out. On substituting the value, I get the value of tangential speed as 5.4985 meters per second. Then I go for tan beta 2. Tan beta 2 is Vf2 or V2 divided by U2. So already Vf2, we have found out this one, Vr1 is equal to Vf1, V2 is also given in the question. So on substitution and simplification, I get the value of beta 2 as 36.03 degrees. So therefore, sine beta 2 is equal to the next term. That is, we can find out the relative velocity for the outlet velocity triangle. That is this one, VR2, using this velocity triangle at the outlet. Sine beta 2 is equal to opposite side V2 divided by VR2 or VF2 divided by VR2. On simplification and substituting the values, I get the value of VR2 as 6.8 meters per second. Once all the velocity terms and angles are known to you, then go over finding for the terms which you have asked. That is the blade angles which we have found out. Beta 1, beta 2 is already found out. Power developed, P is equal to m dot E using the energy equation. And before that, we need to find out the mass flow rate. And regarding this, he has given in the question that there is some of the width for the impeller. So what we'll do is we consider this equation m dot is equal to rho pi d1 b1 into vf1, where density of water is 1000, d1 breadth is given as width is given as 0.12, vf1 is 4. We get the mass for it as 904.896 kgs per second. Go for the energy equation, u1 u2 we have calculated, and from the picture you can see clearly that the value of vu2 is 0, which means this entire term becomes 0. We are left with u1 vu1 by gc. On substitution and simplification, and you can see already in the picture also here for the inlet velocity triangle, that is u1 is equal to vu1, means both the values are the same. On substitution and simplification, I get the value of E as 120.934 joules. Substitute in the power equation, and the value of power is 109.432 kilowatts. Similarly, our degree of reaction equation, already we have discussed R equation. So how we are writing generally our degree of reaction equation? R is equal to E minus of V1 square minus V2 square by 2gc whole divided by E. Using this equation, we can find the value of R, and the value of R is, it's around 0.5006, that is 50% reaction. This is the solution for this particular. This is the solution for this particular problem. Now, similarly, another one type of problem is given here. Let us see here. That is, yes, it says, in a mixed flow turbo machine means water fluid may enter tangentially, it may leave axially, or any other conditions of flow may be there. He says the fluid enters such that the absolute velocity is axial. The absolute velocity is axial at the inlet. So at the inlet there is axial velocity, and at outlet relative velocity is radial. So here both the conditions are given again in the problem itself. What is the degree of reaction and energy input into the fluid if the relative velocity at outlet is same as tangential speed at inlet, with inlet diameter 16 centimeter and exit diameter 50 centimeter, tangential speed is 3000 rpm, and blade angle at inlet is 45 degrees. First we shall sketch the sketch of an inlet velocity triangle and outlet velocity triangle. So this is a sketch of the inlet velocity triangle, students. Just I will draw the generalized structure. Then with respect to the conditions, we can change the shape of the inlet velocity triangle. Alpha 1. This I have VR1. This I have beta 1. U1. Then I have VU1. This is VF1. If you read the statement carefully, he has said that the fluid enters such that the absolute velocity is axial. Absolute velocity is a thing, but it is this particular term, that is V1. This velocity is axial at where? At the inlet conditions, he has said. So therefore, this V1, it overlaps on which one? The flow velocity, that is VF1 is equal to V1. And the new velocity triangle is VF1 is equal to V1. Here we get alpha 1, which means it is equal to 90 degrees. And this term is vanishing. This is disappearing. So when this is disappearing, then what happens? You can see that u1 value, it is now here. This is u1 value and v1 equal to 0. So therefore, the new sketch of the inlet velocity triangle, it is in this fashion now according to the given condition. Absolute velocity, then it is axial. V1 is equal to Vf1. This is alpha 1, which is equal to 90 degrees. Vr1, beta 1. This is u1. And as V1 is equal to Vf1, so V1 is equal to 0. This is for the inlet velocity triangle. Similarly, for the outlet velocity triangle, let us see here. This is the generalized structure which I am drawing here. This is Vr2, beta 2, V2, alpha 2. This is U2. This is VU2. And this is VF2. He says outlet relative velocity is radial. Outlet relative velocity is nothing but it is VR2. This is radial, means this is overlapping on this VF2. So when this is overlapping on VF2, the new outlet velocity triangle, which is in this fashion now, see here. VF2 is equal to VR2, outlet velocity is radial. Then we are remaining with V2. This is alpha 2. This is beta 2. This is U2, which is also equal to VU2. These are the conditions for the outlet velocity triangle. Okay. Then he says another important thing in this problem is we need to find the value of degree of reaction R. Energy input to the fluid. Please remember, students, energy input to the fluid means they are the power absorbing machines. And for power absorbing machines, the equation we write it as E is equal to U2 VU2 minus U1 VU1 by GC. Then he says the rate velocity at the outlet VR2 is same as tangential speed at inlet. Tangential speed at inlet is nothing but it is U1. With inlet diameter, he has given directly can take care, no problem, because he has not mentioned regarding the type, whether it is inward and outward. He has mentioned the mixed motor motion. So we can take directly D1 as 16 centimeter, that is 0.16 meter, and exit diameter D2 as 50 centimeter, that is 0.5 meters, with a tangential speed of 3000 RPM, that is the value of N which is given to us. And a blade angle at inlet, that is beta 1, he has given it as 45 degrees. With this condition, we need to find the solution of the problem. Let us start the point. The given things, we draw the inlet velocity triangle with the conditions. As he has said here in the conditions given in the problem, absolute velocity is axial, that is V1 is equal to Vf1, which you can see here, I have done here. Alpha 1 is equal to 90 degrees by default. And blade angle at inlet is 45 degrees, that is this beta 1, it is 45 degrees. Similarly, I draw the outlet velocity triangle, and as I have said, for outlet velocity triangle, outlet velocity is radial, which means you can see here, this is radial directions, beta 2 is equal to 90 degrees, which you can see here, U2 is equal to VU2. Then we write down the conditions, and let us start with the solution part. So finding out the trigonometric functions for both the inlet and outlet velocity triangles along with the velocity terms. Beginning with the inlet velocity triangle, we have tangential speed U1 is equal to pi d1 n by 60. D1 is already given to us. On substituting the value of n and simplification, I get the tangential speed as 25.136 meters per second. Once U1 value is known to us, beta 1 is also given to us, we can find the value of V1 and Vf1 also. Or you can use your Pythagoras theorem to find the value of Vr1 also. But I will go with the cos beta 1 trigonometric function. You can use that method also. Cos beta 1 is equal to U1 by Vr1, where the value of Vr1 we get it as 35.547 meters per second. Similarly, tan beta 1 is equal to V1 by Vu1, where beta 1 value is known to you, U1 value is known to you. You can find the value of V1 from the inlet velocity triangle. On substitution and simplification, I get the value of V1 as 25.136 meters per second. Next, I go for the outer velocity triangle. In the outer velocity triangle, already we can see from the figure that beta 2 is equal to 90 degrees. You can find out the value of U2 here using the equation pi d2n by 60, and we get the value as 78.55 meters per second. And as you can see in the sketch that U2 and Vu2 are equal, so we can write U2 is equal to Vu2. Then using the trigonometric function, tan alpha 2 is equal to Vr2 by U2. So already Vr2 value is known to us. Sorry, the U2 value is known to us. Tan alpha 2 is equal to V1 by U2, because we take the conditions that beta 2 is equal to alpha 1. Students, if you observe here in the sketch carefully, the value of beta 2, this beta 2, it is 90 degrees. Also, the value of alpha 1, this is also equal to 90 degrees. So therefore, I can write in place of Vr2 this as V1. And on substitution and simplification, I get the value of alpha 2 as 17.74 degrees. So next, as the conditions, as I said, alpha is equal to V1 is equal to Vr2 is equal to 25.136 meters per second. Similarly, I go for finding sine alpha 2 using the trigonometric function of sine alpha 2 for the outlet velocity triangle, for the outlet velocity triangle, using sine alpha 2, that is Vr2 by V2. On a substitution and a simplification, I get the value of V2 as 82.49 meters per second. So 82.49 per second. Therefore, energy input to the fluid equation, that is U2 Vu2 minus U1 V1 by GC. As from the figure, you can see that Vu1 is equal to 0. Then this term becomes 0. You are remaining with U2 Vu2, and U2 and Vu2 are both equal to one another, which means U square by GC. On substitution and simplification, I get the value of V as 6.1701 kilojoules. Go for finding the degree of reaction equation. Please remember here the degree of reaction which you are finding. You should write here V2 square minus V1 square by 2GC here. Why? Because this is the equation for which one? Energy input to the fluid. So here you also have written U2 V2 minus U1 V1 by GC. Therefore, it should be V2 square minus V1 square by 2GC. If you write V1 square minus V2 square, your answer is wrong. On substitution and simplification, the value of R we get it as 0.499 or nearly around 50%, you can say. So these are some of the problems on the radial flow studies. These are some of the problems in the radial flow studies. Similar problems are there. We can go for many number of problems. You can visit some of the previous question papers, the gate question papers. You will get such kind of problems. If you have any doubts, you can send me an email to the email ID which you have left on the first slide itself, and you can send me some videos and you can send me the comments also. Thank you, students.